So here we have our design objectives that we determined last time. And so just try to quantify these with some criteria. And so for cost, how much do we think that we wanted to cost our device to cost?
So looking on Google, I think the cost of an infusion pump, which they use in the US, is like less than $1,000.
Okay, so that seems really high, especially because it's for the developing world. Yeah, I've read that they actually only spend about $2 a person on healthcare. So
Would less than $100 be good then? Especially if we're working with the developing world?
So after talking to our clients, Dr. Richards Cordham and Dr. Odin, they suggested that something like $20 to $30 might be reasonable
Alright.
for these developing countries.
okay, so let's try and
20?
get 20. Yeah,
Yeah.
That's good.
let's go for it. Yeah.
And for weight then, how heavy can we let it be?
Well, if you think about a medical device that's going to be probably carried around, and then you have nurses in developing countries that are going to be using them, we want it definitely under a certain amount that can be carried, so under 10 kilograms for sure.
I think
But if you think about like when you go to the gym, you want it probably around the weight of a dumbbell as well. So maybe hit around 2 or 3 kilograms. Do you
okay.
think that would be good?
Yeah, I think that's reasonable.
Yeah.
Okay.
So around 2 kilograms. I think that's what we want to shoot for sure.
Okay. Ease of use. So this is going to be, I guess, how easy it is for somebody to use the device. How do you quantify that? How do you?
I guess there could be a couple of different ways we could do it. We could do like look at the amount of time it takes, or even like the number of steps it takes to like set up the device, whatever it is.
Yeah, we have to consider like the educational level of the end users. So they're in developing countries. They might not even be literate. So there's a lot of things to take
Yeah,
into
that's a
account.
very broad amount of aspects that we're going to be defining. So I think if we went more towards the user-based scale to define ease of use, I think that might be better.
Yeah.
We should probably come back to that since it's a bit
Okay.
harder to define in numbers.
Let's put user-defined scale for now.
Yeah.
Yeah, that's fair.
Yeah, so we want to be, actually, you should be within a certain range of the target. So for maybe children, sometimes they may only need 200 milliliters of fluid. And so we want to be around that range. If you're maybe like within 100 milliliters, but then within 100 milliliters maybe, but so like between one. So if we wanted to give them 200, it'd be between 100 and 300.
That's a
That
bit
seems
high.
like a
Yeah.
really big range.
Yeah, it does.
So maybe something smaller, like 50 or even 20 milliliters.
Okay, yeah, I don't see anybody being hurt with just maybe 20 extra milliliters. So I think that would be a safe amount.
20 mils.
Just thinking about the size of a child, I think that.
Yeah.
And then do we want that to be 20 mils across all volume suspense? Because if we did like a percent, do you think that would be better? No.
So if you had like 800 milliliters, and then say you do like if it was a percentage, it would kind of accumulate the air,
Oh, you're right.
accumulate
Yeah.
and contribute to
Okay.
dangerous
Oh, yeah.
volumes. So I think we should keep it as a volume of
Yeah.
I'd say
So-
20 milliliters.
So less than plus
Less
or
than-
minus 20 mils.
Yeah.
Oh, yeah.
That's good.
Yeah. Durability. So the device is going to be moved around. How often do we think it's going to be used?
If we're going to be selling it or giving it to, I guess, low resource settings or in the development world, I think they wouldn't want to buy it too often. They would want to like have it last a long time. So maybe around 10 years. Do you think?
That seems like a little much because it's really hot and humid over there. So like whatever we make will probably start degrading pretty quickly.
Yeah, and if they use this device a lot, let's say they use it maybe 3 times a day, it might not last up to 10 years. And if they're moving it, something, it has to be able to withstand movement. So maybe we think that we can get it within 10 years seems high, so maybe cut that in half like to 5 years.
Seems all right.
Yeah, so 5 years at the least. Okay, So
So I think one thing that I read about was one way to quantify reliability is like a failure rate, like X times in like 100,000 uses.
okay. So how reliability would be quantified by things going wrong? Like
Yeah.
we want to minimize that.
Yeah, so like how many times would we do it?
I mean, since a patient's life is at stake, I would
Yeah.
hopefully 0, but I guess that's not very realistic.
Yeah, that's impossible to have a 0% failure rate. Well, if you're going with 100,000 uses, maybe 10. Do you think 10 is too much?
That might be a lot. That's like
10 people.
Yeah.
I would try maybe 1 if we can.
Yeah.
So, okay, get as close to 0 as possible. So what we've done is we've taken our objectives and we've turned them into measurable design criteria that we can use when making decisions about how we're going to engineer this device. So we said we want our cost to be less than $20 and the weight of each device to be less than 2 kilograms.
And then when we came to ease of use, we thought it would be more suitable to have a user-defined scale. And then when we came to accuracy, we wanted something that was under plus or minus 20 mils instead of an actual percent of IV fluid dispensed.
As for durability, we decided on something that lasts more than 5 years. And for reliability, we quantified that as a failure rate of less than 1 failure per 100,000 uses.